So now that we have learned quotient groups, my next topic is to do what are called isomorphism theorems. These are very important theorems that tell you how to understand if groups are isomorphic, and if groups are isomorphic, then what implications do they have. So, and all this uses the notion of quotient groups. So the next goal is to study isomorphism theorems for groups. So there are three such theorems. In this video I will do the first isomorphism theorem and I will illustrate it with one example, and in future videos we will do the other two isomorphism theorems. So first isomorphism theorem says the following. Okay, so there are three such isomorphism theorems. We will do the first today. First isomorphism theorem is the following. Let phi from G to G prime be a group homomorphism. The first isomorphism theorem says that in this situation we have the following. Then we have a group isomorphism from G mod kernel of phi to image of phi. Okay, that's what the first isomorphism theorem says. It's a good time to recall what is an isomorphism. An isomorphism is any group homomorphism which is bijective as a set map. Okay, so isomorphism allows you to think of these two groups as essentially the same groups. If you have a group homomorphism, kernel in order to even make sense, remember I am saying that this is a group isomorphism. So these two are groups in particular. Image phi is a group that we know because it's a subgroup of G prime, but G mod kernel phi is also a group because in general the quotient is only defined when you have a normal subgroup. But remember, kernel phi is a normal subgroup of hence we can talk about G mod kernel phi as a group. So G mod kernel phi is isomorphic to image phi. This should remind you a problem that we have solved in an earlier video, where we have shown that order of G is equal to the product of order of kernel phi and the order of image phi. That is just a purely set theoretic statement. Number of elements of G, and that required you to deal with a finite group, right? Because the number of elements of G needs to be finite for that statement. Is the number of elements of kernel phi times number of elements of image phi. But this is a very general result. This has nothing to do with finite groups. And here we are only talking about isomorphisms. And in particular, the problem follows from this if you think about it. Because these two are isomorphic groups means the orders are same. And order of G mod kernel phi is order of G divided by order of kernel phi. Okay. So the proof of this theorem, let me give. It's very simple. It is essentially the problem that we have solved. In the problem we have constructed a bijection. Now we will simply show that that bijection is actually a group homomorphism. Consider the function I think I called the group homomorphism phi, so let's call the function f. I think this is what we have done in that problem also. And the function is the same. What is the function? You take an element of this which is of the form a times kernel phi. So I think it's probably better if I use letters like before. So I'm going to rewrite this as G mod n to h prime. And what is this? This sends a n to phi a. From a problem earlier, we know that phi is bijective, right? In that problem we have exactly shown that it's bijective. It is certainly onto, and if two cosets map to the same element, that means those cosets are same. So we only need to now show that F is a homomorphism, because a bijective homomorphism is an isomorphism. So we only need to show that F is a homomorphism. What does this mean? Now, in other words, we have to show that FAN times BN is, want to check FAN times FBN, right? We want to check this. So let's check both sides. What is FAN times BN? This is same as FABN, because that's the product in the quotient group. AN times BN is ABN. And what is this? FAN is phi of A and FBN is phi of B, right? And what is FABN? You take any coset and you take the element here and map it to phi of that element. So it is FABN will be phi of AB. Now is this true? Phi AB is phi FEB? Of course it's true. This is true because phi is a homomorphism. So we have, and hence F is a homomorphism, right? So we have checked that F is a homomorphism. So the proof is done. So F is a bijective. Bijective comes from before, that we have checked before, and we checked today that it is homomorphism. It is a bijective homomorphism. So F is an isomorphism. That's it. So F is an isomorphism, and hence we have G mod kernel phi. This is my notation, this symbol here, arrow with this sign symbol here, to indicate that we have an isomorphism. Okay, so that's the proof of the theorem. First isomorphism theorem is proved. Okay, so it says that if you have any group homomorphism, there is an isomorphism between the quotient group G mod kernel phi and the image group. Okay, so why is this useful? So as I said, first isomorphism theorem and more generally all isomorphism theorems are very useful in determining properties and observing new facts about groups. So let us explore this in one example. So I'm going to recall for you what we have done in a previous video. We recall that if nz is a subgroup of z, okay, actually what we should write is for any n in integers, the quotient group z mod nz is cyclic. This I did in the previous one of the previous videos, where after we talked about quotient groups, we explicitly calculated quotient groups for subgroups of Z. So in particular, Z mod nz we concluded was cyclic. I left the last part for you to check as an exercise. Now we will now show a sort of converse for this. We will now show that any cyclic group is isomorphic to Z mod nz for some n. And this is a very remarkable statement, right? It's okay to say that Z mod nz is cyclic. That is just a statement about subgroups of integers and quotient groups. Now we are saying that you take an arbitrary subgroup, cyclic group. So, this cyclic group can be anything, nothing to do with Z to begin with. However, it is isomorphic to Z mod nz for a suitable integer. So let me prove this theorem. If G is a cyclic group, then there exists an integer n such that okay, so this symbol here, my notation I should remind you, we write G with the symbol to mean G is isomorphic to G prime. Okay, that's my notation. So I'm saying that if any cyclic group is isomorphic to this, so this is a very it's to be thought of as a structural theorem for cyclic groups. Any cyclic group is of this form. So if you understand these groups, then you understand all cyclic groups, right? That's the meaning. So what is a proof? Proof is an immediate application of the first isomorphism theorem. So let's proceed this way. Let A be a generator of G. Remember, G is a cyclic group. That means it is generated by a single element, right? So G is this is what it means. Powers of A cover all of G. This is what it means, because such a thing exists because G is cyclic. We are assuming that G is a cyclic group. So there is an element A such that its powers span or cover all of G. So you have A power n equals the set A power n as n varies over integers is equal to G. Now consider the function phi from Z to G. Okay, so yeah, so consider the function phi from Z to G. What is this function? It takes n to A power n. So this is a function that we have studied in the past in a previous video. So we have seen earlier that phi is a homomorphism. Okay, so a quick recall. Remember, we are defining phi n is A power n. We want phi of n plus m. This is by definition A power n plus m. This is same as a n a m. Okay, that is if you write A product with A itself n times and m times, you pool them, you get n plus m times, and that is same as phi n phi m. Okay, so this is not difficult at all, right? So phi is a group homomorphism. So not only that, so phi is a group homomorphism. So phi from Z to G is a group homomorphism. And this is the first point. And of course phi is onto. See, this is the meaning of B. This is because G is cyclic. G is generated by, the point is phi maps an element, an integer n to A power n. In general, the set of elements A power n as n varies is not all of G. That happens only if G is generated by A. So G is generated by A, so phi is onto, because every element of G is of the form A power n. Now what is the kernel? So is that clear? Phi is onto because G is generated by A. Every element of G is A power an integer. So phi is onto. Kernel phi, whatever it is a subgroup of Z. Right? In general, kernel is always a subgroup of the group, domain group. So suppose, and what are the subgroups of Z? And what are the subgroups of Z? We know that subgroups of Z are, they are of the form Okay, so I should use some new letter maybe, but hopefully it's not confusing to use n again, because, though we have used n to denote an arbitrary integer for, right, they are of the form nz. So suppose, now coming back to our specific kernel phi is nz. Okay, so let's summarize what we have. So we have a homomorphism, group homomorphism phi from Z to G such that phi is onto and kernel phi is nz. Now let's think about what first isomorphism theorem says. What does first isomorphism theorem say? What does it say? First isomorphism theorem says so let's see what it is. First isomorphism theorem said if phi is a group homomorphism from G to G prime, then we have an isomorphism from G mod kernel to image phi. So we are done now. Let's apply that to our. So we have Z mod kernel is isomorphic to image phi, but the kernel is nz, so Z mod nz is isomorphic to, because phi is onto, image phi is all of, right? So phi is onto means image phi is G. So Z mod nz is equal to isomorphic to G, which is exactly the theorem that I wanted to prove. So we wanted to prove that any group, any cyclic group, if G is a cyclic group, there exists an integer n such that G is isomorphic to Z mod nz. We have shown that, right? So this completes the proof of the theorem. So first isomorphism theorem is a very simple statement really, because its proof is clear, but it's a very powerful result. It comes up all the time. It's a very simple observation, but it's always repeatedly used in various situations, and using it we have proved a remarkable theorem that any cyclic group is isomorphic to Z mod nz. Why do I say it's remarkable? Because G is an arbitrary cyclic group. G could be anything. G is something that we do not know what it is. However, we have identified with a very specific, well-known, easily understood group Z mod nz. So this is to be thought of as the conclusion to be drawn from all this is the following. Using isomorphism theorems, we can essentially isolate the important properties of cyclic groups and think of them as Z mod nz. There is nothing more. So let me give you one example to illustrate this. So let G be the group of fourth roots of unity. What are they? This is a group that we have seen before. This is 1, I being a square root of minus 1, right? Complex square root of minus 1, minus 1, minus I. We have seen before that G is cyclic and it is of order 4. So actually, yeah, so G is cyclic of order 4. So by the theorem, G is isomorphic to Z mod nz. So Z mod 4Z. So I should have been more precise in my statement of the theorem. I wrote here G is a cyclic group, then there exists an integer n such that G is isomorphic to Z mod nz. But what is n actually? N cannot be an arbitrary number, n has to be related to G. Here n is order of G, right? So what we can conclude is that y is it equal to n, what is the point here? So y is it equal to, y is n equal to order of G, because if you go back and see, kernel will be nz. So what I said is kernel is a subgroup of z, so it is nz, but what is that n? It is the least positive integer such that a power n is identity, which is exactly the order of n. So n is the order of a, which is the, because a generates G, order of a is cardinality of G. Okay, so in this case G is isomorphic to Z mod 4Z. So to be precise, what we are doing is consider the map from Z to G. We send any integer to I power a. So the kernel of this is precisely 4Z, because kernel is the set of integers such that I power a is identity, in this case 1. So I power 4 is 1, I power 8 is 1, I power minus 4 is 1, and so on. So Z mod okay, so the theorem really written in a more precise fashion is, if G is a cyclic group of order n, then G is isomorphic to Z mod nz. Okay, so let me stop the video here. We have seen a very important theorem here called the first isomorphism theorem, and if you go back and see the statement and its proof, it's not difficult at all. However, it is always used, it is an important property of group isomorphisms that comes up a lot. So, and we have seen one example of it where we conclude that any cyclic group of order n is isomorphic to Z mod nz. So let me stop the video here. In the next videos we will study the second and third isomorphism theorems. Thank you.